The deep dive is open, and today we're stepping into one of the most high-risk environments on any vessel: hot work.
Welding, cutting. I mean, you're dealing with sparks and flammable gases in a steel box.
Exactly. The stakes are just sky high. Fire, explosion, toxic fumes, all very real threats. So we've taken a whole stack of regulations to give you a shortcut, really, on safety compliance for your stationary gas distribution system, your GDS.
And we're going to get really specific. We're talking about the acetylene oxygen, or ACOX manifold systems, whether they're on the main deck in a storage room or, at the workshop outlets in the engine room.
This isn't just about ticking boxes, is it?
No, not at all. It's about
No.
getting the philosophy behind the compliance. If
Right.
you're managing maintenance, if you're facing audits from Sire or Right Ship, this is essential stuff.
Okay, so here's our mission. We're going to unpack the whole safety framework, all the component details, but there's a big point of tension here we need to hit right away.
The 5-year rule.
The 5-year rule. It's this critical replacement schedule, but it's not calculated from the day you install a part.
No, and this trips people up all the time. It's calculated from the date of manufacturing, the DOM.
So the clock starts ticking months, maybe even a year, before that component ever gets to your vessel.
Right. And that little detail, Dom, is what separates a pass from a failure in an audit. But, before we even get into those timelines, we have to start with the absolute foundation.
The room itself.
The room itself,
Oh.
housekeeping, the prohibitions, the basics that keep the system stable.
Okay, let's start there. The physical space, compliance, I guess, starts with the sign on the door.
It really does. You need clear, mandatory signage, no smoking, no non-authorized access, and of course gas identification. But it's inside the acetylene compartment where it gets, incredibly specific.
And that specificity really tells you something about how dangerous this gas is.
It tells you everything. Acetylene gas fires are exceptionally difficult to deal with. So the sources mandate 2 very specific emergency items for that space.
Okay, what are they?
First, a dedicated spanner. It lives in that room, and its only job is for the quick disconnecting of the high-pressure hoses if you need to isolate a cylinder fast.
Okay, a dedicated tool. And the second item, this one really stood out to me.
A heat-resistant mitten or a heavy-duty glove. And it's there for one reason: to let a crew member physically grab and try to close an acetylene cylinder valve that is on fire.
Wow, just wow. Needing a special glove just to turn off a burning cylinder? That one item tells you the whole story about the risk.
It absolutely does. And beyond the emergency gear, the storage itself is just as strict.
Oh, so.
Well, cylinders have to be secured in racks. Critically, no lashing is allowed. The securing method has to allow for a quick release in an emergency.
Right.
And they can't just sit on the deck. They have to be on a slightly raised metal crossbar. This helps prevent corrosion, sure, but it's also essential for proper earthing.
And of course, separating the full and the empty cylinders and always keeping those top safety caps on when they're not in service.
All standard, but critical discipline.
So we've secured the cylinders. But sometimes the biggest danger is something you might add to the system, like a bit of grease or sealant. And this is where it gets really counterintuitive for a lot of people.
Ah, yes, the forbidden materials list. You are strictly, and I mean strictly, prohibited from putting any grease, wrapping, coatings, or even paint on the GDS piping, even if you're trying to stop rust.
So why that zero tolerance policy on grease?
It's fundamental chemistry. Any kind of oil or grease, any hydrocarbon that touches high-pressure oxygen can just spontaneously ignite. It's called an oxidant reaction, an explosion waiting to happen.
I see. And the same logic applies to something like Teflon tape.
Precisely. No sealing tape on threaded joints. Only metal-to-metal sealing is allowed. You just cannot risk introducing any material that could become fuel in an oxygen-rich environment.
Okay, and that brings us to the big one. The absolute ban on a very common metal, copper. Why is copper so dangerous around acetylene?
This is a different, but just as serious chemical hazard. Acetylene can react with pure copper, and silver for that matter, to form unstable compounds called acetylides.
And these are explosive.
Highly explosive. So it's zero tolerance, no copper washers, no copper adapters or tubing, nothing.
So if you can't use copper, what do you use to seal those high-pressure connections?
The sources are very clear. Aluminum washers for the oxygen hoses and nylon washers for the acetylene hoses. And here's the key discipline. You replace those washers every single time you disconnect the hose. It's a tiny cost for major insurance.
Right. And finally, there's a crucial operating rule. It's not about what you use, but how you do something. It's about the speed of your hand.
Yes. When you open the cylinder top valves for both oxygen and acetylene, you have to do it very, very slowly.
And this is to prevent something called adiabatic compression.
Exactly. If you let that high-pressure gas rush into the regulator, the sudden compression generates a huge amount of heat, hundreds of degrees. It can easily ignite any tiny particle of dust or contaminant inside and cause a catastrophic failure, an explosion.
So open slowly isn't just advice, it's a critical safety step to prevent a physics-based detonation.
It is.
Yeah.
And then when the work's done, you always release the residual pressure from the whole system. Don't just walk away.
Okay, that covers the foundation. Now let's get into the heart of the regulatory challenge. The components themselves, starting in the central manifold rooms. This is where that 5-year rule really bites.
It really does. Sire, Right Ship, CP7. They all mandate that critical components, so we're talking regulators and flashback arrestors, must be replaced every 5 years.
5 years from the date of manufacturing, the DOM, not from when you installed it.
That's the part that changes all your maintenance planning. Let's start with the high-pressure hoses. They connect the cylinder to the manifold. They're exposed to sun, salt. They have a tough life.
So they wear out quickly.
Typically 4 to 5 years. And they must have clear labels showing their manufacturing date and pressure test details. If that DOM is more than 5 years old or you see any damage, it has to go. No questions asked.
Okay, next up, the central gas pressure reducers. The regulators. This is where just grabbing any old regulator off the shelf can get you in serious trouble.
Absolutely. The central regulators have to be for manifold systems. The standard is ISO EN 7291. You're looking for a heavy-duty model, like an R520.
What you can't use is the common EN ISO 2503 type, right? The one you see on a single bottle in a workshop.
Correct. And that's a huge point of failure in audits.
So why? Why is that standard 2503 regulator so dangerous in a central system?
It's all about how it's designed to fail. A manifold regulator like the R520 is built for a permanent installation. It has a secure nut on the knob so the pressure can't be accidentally changed. But the most critical part is a special relief valve outlet.
A vent pipe.
Exactly. It has to be connected to a vent pipe that safely routes any overpressure gas out of the compartment. Your standard workshop regulator just doesn't have that. It would vent high-pressure gas right into the room.
Okay, so it's designed for system protection, not just single bottle use. And these need more than just replacement every 5 years. They need annual checks.
They absolutely do. Every year, both the operating and the spare regulators have to pass a creep test.
A creep test, what's that checking for?
It verifies that high-pressure gas isn't creeping past the internal diaphragm into the low-pressure side when the regulator is shut off. If it fails, you could be overpressurizing your entire downstream system without even knowing it.
A silent but very dangerous failure. Okay, let's talk about that last line of defense. The central flashback arrestors, the FBAs.
These are the heavy hitters. High capacity, and for the central system, they must be the non-resettable type.
Non-resettable, so if it triggers, the whole unit is basically sacrificial. You have to throw it out.
Precisely. In a big central system, you don't want anyone trying to reset a device that might be internally damaged. A flashback is a major event. You want it to lock down permanently, forcing a full replacement and inspection.
And these also have the 5-year DOM rule and an annual test.
Yes, they have a 5-year replacement rule, and they need an annual backflow test to make sure that crucial non-return valve is still working perfectly.
So it sounds like being ready for an audit just comes down to the crew being able to find and read those manufacturing dates, and they're not on a nice, clean sticker.
Not at all. You're looking for tiny, hard-engraved date codes stamped on the back plate of the regulator or on the body of the arrestor, and those cryptic little numbers are the official clock. Get that calculation wrong, and you fail the audit. It's a very common and costly mistake.
Okay, let's move out of the central room and down to the engine room workshop. The point of use. The rules change a bit here, don't they?
They do. The components are designed for more localized intermittent work. So, for example, the outlet regulators usually only have one pressure gauge for the working pressure, not the two you see on the central ones.
But they still have the 5-year replacement rule.
Still the strict 5-year DOM rule, and they still need that annual creep test. The risk of overpressurizing the torch equipment is still there.
How do the flashback arrestors differ at the workshop outlet?
The key difference is that these must be resettable. The SF55 type is a common example. They do all the same safety functions, but they also have what's called a pressure-sensitive cutoff valve, or PV.
So if you get a small flashback at the torch, the local arrestor trips, you can reset it and get back to work.
Exactly.
Whereas if the central one trips, you're shutting down the entire system for a major inspection.
That's the design philosophy. The central arrestor protects the whole pipeline with a permanent lockout. The outlet one provides localized protection and, allows for continuity of work after a minor incident. But, it is a big but, they both have the same 5-year DOM rule and annual backflow tests.
And we've seen some pretty dangerous workarounds in the sources. What are some common non-compliant things people do at these outlets?
A big one is using cheap ball-type water tap valves as gas shutoff valves. They are completely wrong for this kind of service. Or using any component that doesn't have a visible EN or ISO conformity mark and a clear production date. If you can't prove it's the right part and it's in date, it's non-compliant, period.
Okay, last piece of the puzzle. The stationary piping itself, the pipes running from the central room to the workshop, this is really critical during, say, a dry dock.
Right, this is about structural integrity.
Yeah.
And the rule is simple. Connections in the low-pressure hard piping must be butt welded.
No threaded joints, no flanges.
Absolutely not. Threaded or flanged joints are a major leak risk. They're prohibited by standards like BCG ACP7. It has to be a permanent welded system.
And how should that piping be secured?
It has to be secured with non-conductive pipe clamps. You can't use standard metal U-bolts because you don't want to create an electrical circuit risk.
Right.
And where the pipe goes through a steel bulkhead, it has to use special insulating bushes. You can't just weld the pipe to the bulkhead. Oh, and no negative loops or dips in the piping.
Why no dips?
Because they can collect moisture or residue over time, which can lead to internal corrosion and compromise the whole system.
So this deep dive really shows that GDS safety stands on 3 pillars. You have the strict housekeeping.
No grease, no copper, slow valve openings.
Then you have the correct component selection and that meticulous 5-year renewal from the date of manufacturing.
And finally, the structural integrity of the welded pipeline itself.
So to wrap it all up, the single most critical discipline, beyond all the hardware, is the paperwork.
It really is. Your logging and record keeping. Your records must calculate that next renewal due date based only on the component's manufacturing date, not the installation date. That's what auditors live and die by.
And the sources are clear that it's the crew, the people on the vessel, who have the sole responsibility for getting this right, for interpreting the rules, for buying the right spares, for handling the liability.
Which brings us right back to that central tension we started with.
It does, and it leaves us with a final thought for you to consider. If you have a crucial, expensive safety component, like a high-end regulator, and your annual creep test shows it's working perfectly, it probably has a safe lifespan of 10 years or more. But the regulations demand you throw it away after 5 years from the day it was made. So how do you, on a vessel, balance the real-world utility and the cost of that equipment against the absolute non-negotiable mandate of strict regulatory compliance?
That's a tough one.
Something to mull over as you check your own maintenance records. We'll see you next time on The Deep Dive.